All right, so what we're going to be doing tonight, I'm going to be looking at rational functions. And when you think about rational functions, and by this is section 6.1, we're talking about functions that are a ratio of other functions. So when we think rational functions, think ratio. So what typically is going to be the case is we're going to have one function divided by another. So we can have a function, say, f of x divided by g of x. We're going to be looking at things like this. Or sometimes with the notation will go as oftentimes p of x over q of x. So with now more specifically, when we're talking about rational functions, we're talking about ratios of polynomials. So what we learned in the last chapter about factoring polynomials, that's going to become useful in this section as well. So let me give you an example of some rational functions. So something like this. This would be a rational function. Or you could have something like this. Let's see. Oh, this is one here. So we could have something like this. This would be a rational function. This would be a rational function. Two different rational functions. So the first thing they're going to ask us to do is domain. Now this hasn't been much of an issue in the past, but it's going to become an issue now. And you can think of domain as this. Acceptable values of x. Now, this is kind of strange. Acceptable according to whom? Well, so far we've mostly worked with lines and polynomials. And when we're working with lines and polynomials, all the values of x are acceptable. I'm going to say other polynomials because technically lines are polynomials. They're degree 1 polynomials where there's only an x term and it has at most degree 1. That invisible 1 is an exponent. So for lines and other polynomials, all values of x are acceptable. So when we talk about the domain, we're talking about all these values of x. And we're usually talking about an interval on the number line. Well, if all the values are acceptable, then the entire number line will work. Now again, this is for lines and other polynomials. So our domain will go negative infinity to positive infinity. Now, what about rational functions, though? This is where we have polynomials dividing polynomials. Well, there are certain things we want to avoid with domain when we're working with real numbers. And there's some complicated functions that have some complicated restrictions. The natural log function comes to mind. Tangent function comes to mind. But when we're dealing with polynomials, the big thing we want to avoid is division by 0. or not for rational functions, I'm sorry, rational functions of polynomials. Polynomials, you don't have to worry about division by 0, but for rational functions, you do. So you want to be careful for values of x that are going to cause the polynomial on the bottom of the rational function to be 0. And these values of x that cause that polynomial, those are not in the domain. So these values of x you want to be careful of, because when they cause a division by 0, we can't have division by 0. It causes all kinds of problems. So we're going to be on the lookout for those. Now, the top polynomial, the one on top, isn't going to be a problem. That can become 0, that's fine. It's the bottom one we got to be careful of. So let me do an example. So let's say we have something like this. You have a degree 1 polynomial, or another term for that could be a line. And then we have a degree 2 polynomial on the bottom. So what we want to do is this. We want to find the values of x that cause this to be 0. And that will tell us which values of x will not be in the domain. But all the other values of x, they can be in the domain. That's perfectly fine. So what we do is we set this equal to 0. Then we factor this. We're going to get this. Now, again, we're going to use the 0 product principle. What value of x would make this 0? Because if this is 0, everything becomes 0. 0 times anything is 0. Well, 0 times any number is going to be 0. Well, this will be 0, 1. X is -3. And this will be 0 when x is 2. So what this tells us, these are the numbers that are not in the domain, but all the other numbers can be in the domain. And again, it's only the bottom polynomial we have to be careful of. This can be 0. If x equals -1, this whole thing becomes 0, and that's perfectly fine. So we're not going to worry about the top, but the bottom here we got to be careful of. So if we draw this, so here's -3, here's 2. Well, we want to leave out 2. And we want to leave out -3. But we also can take everything in between. That's perfectly fine. So long as we leave out -3 and as long as we leave out 2, we're okay. We can take everything smaller than -3, everything bigger than 2, and we can take everything in between. We just can't take -3, we can't take 2. So what this turns out to be, this is -∞ to just short of 3. I'm sorry, -3. This one here is -3, 2, or just above -3 to just short of 2. And then just above 2 to +8. And what we're going to do is we're going to union all these intervals together, because all these numbers are valid. We can dump them into the same box and hand that box to someone and say, these numbers work. So we put in a little union sign, and this will be the domain for our rational function. All right. So let's take a look here. Now, one of the things you can do is you can simplify rational functions. And so the thing with simplifying rational functions is you can essentially reduce them. And in a way, rational functions are going to behave very similar to fractions. So that's what we're going to pretty much be looking at 6.1 and 6.2 from here on out. We're going to basically talk about reducing these, basically a fraction of functions, multiplying them, dividing them, and then adding and subtracting them. And we'll actually have, we encounter this thing called a complex fraction. We're going to have a similar thing here, a complex rational function. So let's talk about the first part, what we might say reducing. Or for rational functions, we'll call it simplifying. So remember with fractions, if we have, let's say 20, let's go with 32. Well, we can break this down into 2 times 2 times 5. And this one, 2 times 2 times 2 times 2 times 2. And so we look for things that can cancel out. That's the shortcut to this, sort of shortcut trick. So 1 for 1, we cancel things out. And then what we're left with is 5 divided by 2 times 2 times 2, or 5 over 8. So that's how we reduce fractions. Now, we can do the same thing with rational functions. So this is what we can do. And again, using our factoring skills, those are going to be helpful. So let's pull one out here. Let's see. So what we want to do is we want to factor the top and the bottom, the numerator function and the denominator function. So in the top here, we can use greatest common factor. And what's common for these two terms is 5. I'm sorry, no, 4. So we factor out a 4. We're left with x plus 5. And if you want to check this, 4 times x is 4x. 4 times 5 will give you 20. Now, in this bottom one here, what's common to these two terms is just x. So just like we can cancel numbers when we reduce fractions, we can cancel these binomials. So these will cancel, and we're going to be left with 4 over x. Now let's get another one here. All right, so let's do this one. Now again, your factoring skills are going to be very important for this. So let's say we have, let's do this one. All right. So we want to factor the top and the bottom. So let's think about the top. Now this is going to be a guess and check method. So you're going to sit down and figure out what two numbers add up to 7 and then multiply to -18. And two numbers that will do that are actually -2 and 9. So this will factor out to x plus 9, x minus 2. This is something you might kind of do off to the side like we've been doing in the other sections. Now for the bottom, again, with this invisible 1 in front of the x squared, this will be a guess and check method. So we want two numbers that add up to -3, but multiply the +2. And those two numbers will turn out to be -1 and -2. So the bottom will factor out to this. So now we factored the top, and now we factored the bottom. So now we put it all back together. And the x minus 2s are going to cancel. So where that'll leave us is just x plus 9 over x minus 1. All right, well, let's take another one. Well, let's say we do this. Now for this one, there isn't anything that's really going to factor out here. That one's done. There's nothing else to do. But let's look at the bottom. Now in this case, we've got a difference of squares. 25 is 5 squared. 9x squared is 3x quantity squared. So you'll square the 3 and you'll square the x. And using our formula for difference of squares, this is a and this is b. 5 minus 3x times 5 plus 3x. So the top here doesn't change, 3x minus 5. We have 5 minus 3x and 5 plus 3x. So let's put it all back together. So the top is going to be the same. This will be 5 minus 3x, 5 plus 3x. Now, it doesn't look like anything can cancel here. But remember from section 5.7, we got a trick. This is positive, this is negative, this is negative, this is positive. Opposite signs, opposite signs. So what we can do is this. We can take minus 3x and factor out a negative 1 to get minus 5 plus 3x, which we can rewrite as just 3x minus 5. So now what we can do, check something here, is double check one more time. Yeah, that's good. What we're going to get is 3x minus 5 minus 1 times 3x minus 5. That's what this thing became. And then we still have, and again, it's addition. We can switch the order with addition. We're going to get this. Now, we're running into a familiar situation with fractions, because what we want to cancel is this and this. Now, remember with fractions when this happens. Let's say we have 2 over 6. When we want to cancel these 2's, we can rewrite this and then we can cancel the 2's to get 1/3. Same thing here. We can take this and rewrite it as 3x minus 5 times 1. We have negative 1, 3x minus 5, 3x plus 5. And now we can do our cancellation. Doot, doot. And so we're left with this. Now, what we can do if we wanted to, and this is a bit pedantic, but you can multiply top and bottom by negative 1 to get this. And again, you can do this by multiplying. And this is just sort of a style thing. You've already solved it when you get to this point. But it's sort of a style thing. Multiply top and bottom by negative 1, so we have the negative on top. And then the way we usually write this, if you remember with fractions, we usually write a fraction like negative 2 over 3. You write it as negative 2/3 like this. Same thing here. We'll do something like that. All right. So there's one thing I do want to mention here, is they mention a little bit about the graphs on these things. And the thing to keep in mind is that when you get a division by 0, if you try to graph a function and there's a division by 0 at some number x on the x-axis, one of two things is going to happen. So for graphs, so the basic rational function, f of x, equals 1 over x. This is one of your canonical functions. Now, when x is 0, you get division by 0. So that means we can't let x be 0. So what you're going to get, you make that note, we get that division by 0 in this case when x is equal to 0. So we're going to get what's called a vertical asymptote. This is sort of a forbidden place. This is where your function cannot cross. There are such things as horizontal asymptotes, but horizontal asymptotes, you can actually cross over those boundaries. But this one you can't. You cannot cross this boundary. So you have this sort of no crossing zone here. And the function does this. And this is what it looks like. Now to generate this function, what you can do is you can do an XY chart. You can say you have like an X, f of x. So let's say x is -3. Well, 1 over x would be 1 over -3, or we write that as -1/3. -2, you get -1/2. Again, using that style with fractions where we move the negative from the bottom up to the top and then out in front, or just out in front if you want to. -1 will turn out to be 1 divided by -1 is -1. 0 is undefined. And then if you have 1, you'll get 1. 2, you'll get 1/2. 3, you'll get 1/3. And if you graph these, you're going to get a shape like this, and then a shape like this, and where x is undefined, you'll have that vertical bar. So this is sort of what this basically looks like. Just want to give you an idea of it. So when you have division by 0, you get these vertical asymptotes. So again, just to give you an idea of what it looks like. This vertical line of the function doesn't cross. So again, just sort of letting you know. When we get to, let's see, we don't do it in this class, but when you get to the college algebra course that comes after this class, we get into how to actually graph these things. I just want to give you an idea of what it looks like. Now, so you get a vertical asymptote. There is a special case when you don't, when a division by 0 does not give you a vertical asymptote. And that happens when the binomial that causes that division by 0 cancels out. But it doesn't quite completely cancel out. Let me explain. So let's say we get this. So let's reduce this thing. So if we reduce it, we're going to get this. If we factor the top, we're going to get x plus 2 times x plus 3. And then the bottom is just x plus 2. So what's going to happen? That's going to cancel. And we're going to get x plus 3. So let me ask you a question here. What's the domain of this rational function? Well, when we talk about the domain of a rational function, we don't think about the reduced or simplified version of it. We work with the function before it's simplified. So determine the domain before reducing or simplifying. So even though this is the equation of a line now, it reduces to a line, and that is true, it does reduce to a line. We don't want to look for the domain of a line. We want to work with the domain when we have the entire rational function here before we've reduced it. So for graphing purposes, we can graph this because it does reduce to a line. So we'll graph this line. But for domain purposes, we better go back to the original function. So in this case, if we set this equal to 0, solve for x, x is minus 2. So this becomes 0 when x is minus 2. So minus 2 is the number we want to avoid. So when we look at the domain, we can take everything below minus 2, everything above minus 2, but not minus 2 itself. So for the domain, that's going to be our answer. This interval union with the interval on the right. So in other words, the interval to the left of -2 union with the interval to the right of -2. So what does this mean for the graph? Well, for the graph, we can use the reduced version. So it's just a line. So it's going to be this. So let me back up a bit. Need a little bit of room. So reduced, we have f of x is now x plus 3. That's the reduced version. Graphing this, it's going to go from here. It's going to go to here. Now, so I'm going to draw this line. So So there's x plus 3. But I'm not done yet. Remember, this is not in our domain. So that means it's not an allowable value for x. So that means where x is -2, there has to be a hole. So the difference between a regular line, say y equals x plus 3, and our reduced function f of x is x plus 3, is that f of x has a restriction on its domain. X cannot equal -2. And that's because of the domain. So x equals -2 is not in the domain. So that means, unlike the line y equals x plus 3, f of x equals x plus 3, this reduced function, has a hole at x equals -2. So just something to keep in mind. You probably will have a chance to graph functions like this, and just keep an eye out for where you're going to need to put one hole, maybe more. So let's see. Well, next what we're going to do, we're going to get into the arithmetic of rational functions, so to speak. And what that's going to mean is looking at multiplication, division, addition and subtraction. And this will carry us into section 6.2. And then I'll show you sort of a slick trick that kind of works with this when you're doing addition and subtraction. But let's take a look first at multiplication. So it's going to be the same as with fractions. So what that means, if you recall fractions, let's say you have 2/3 times 5/7. Well, what we do is we multiply directly across. So you have 2 times 5 over 3 times 7. And you'll get 10 over 21. Now, another thing you can do, you can have something say like this. Again, multiply across. And before we multiply things together, we can see that the 5s are going to cancel. So we can cancel those 5s, and we'll be left with 4/7. So just something to keep in mind when we're doing multiplication. Something else. Again, we just multiply directly across. And what happens here, though, we can break this down. So before we stitch everything up with multiplication, we can write it like so. The 2's will cancel. And so what you'll be left with is 1 over, and then 7 times 3 is 21. So the same tricks we use for multiplying fractions or managing fractions as we multiply them, we're going to use the same thing with these rational functions. So let's see. So let's say we do this. Now, one thing we can do is, and this will help with canceling things, if we can factor first and look for things that will cancel. So we'll factor first what might cancel. So let's take a look at these. X minus 2, x plus 3, nothing's going to factor out of those. I mean, maybe we'll have to factor out a minus 1, but we'll see. But over here, we can factor some things. There's a 2 common to both those terms. So we can factor the 2 out. And then here, there's a 5 common to both these terms. We can factor that out. So as we multiply things together, this is what it's going to look like. X minus 2 times 2 times x plus 3. So that's going to be the top. Now on the bottom, x plus 3 times 5 times x minus 2. So now let's look for things that cancel. Well, first off, x minus 2 and x minus 2, those are going to cancel. And then also x plus 3 and x plus 3, those are going to cancel. So what does that leave us with? Well, it leaves us with just the 2 and the 5. So this reduces, after the multiplication, to 2/5. So it starts out like this, and it simplifies down to that after we multiply. So let's do another one. All right. And let's double check that. Looks good. All right, I think we're good to go. So again, what we want to do is we want to factor things. So I'm just going to kind of go through the factoring kind of quickly, just so we get to the part where we're multiplying, canceling. So x squared minus 9. This is a difference of squares, where we have an x being squared, there's a 3 being squared here. 3 squared will give you 9. So this will become x minus 3, x plus 3. I'm going to work with this first rational function. Now, this you have that invisible 1 in front of the x squared term. This is a guess and check method. And you're looking for two numbers that add up to -1, but multiply to -6. And two numbers that will do that are -3 and 2. So we factored the top and bottom of the first rational function. Take a look at this one. So again, we're going to be using the guess and check method. Two numbers that add up to 5, but multiply to 6. Well, that'll be +2 and +3. Same thing here, guess and check. So two numbers that add up to +1 and multiply to -6. 3 and -2. Now you can start canceling things here. I mean, we have a x minus 3 and x minus 3 that'll go away. Here's a x plus 3 and x plus 3 that'll go away. So now we multiply together what's left. So this will become our new numerator. And down here, we have our denominator. And then look for anything that will cancel. So that'll go, that'll go. And that's going to be your answer. So we handle multiplication a lot of the same ways we do fractions, and we want to break our numbers into prime numbers and look for cancellation before we multiply everything together. The same thing here, in the same way we break things like numbers into products of primes. We're going to break these down into products, in this case of binomials, and then we look for binomials that will cancel. And sometimes it might be not be a binomial that cancels, it could be a trinomial that cancels. All right. So the next thing I want to look at is division. So again, it's going to be similar to fractions. So let's say we have, say, 5/9 divided by 1/7. Now we can use our mnemonic called KFC, which is we keep the first fraction. We flip the second fraction, and then we change the division into a multiplication. We keep, we flip, and we're going to change. So we'll keep this one. We'll flip this one and make this a multiplication. And now that it's a multiplication here, I'll use the dot because we've been using the dot. We multiply directly across. So this will be 35. We'll get 5 times 7. 9 times 1. And there's nothing that's going to cancel here. I mean, we could break this into 3 times 3, but this is a prime number, this is a prime number. 3 and 3 are prime numbers, but 5, 7, and the 3's are not going to cancel. So we're just going to get 35 over 9. And that's going to be our answer. So when it comes to rational functions, same thing. So let's say we have this. So just like we used our KFC for fractions, we're going to do the same thing for rational functions. We're going to KFC this. So we'll keep the first rational function. We'll flip the second. And we'll change the division into a multiplication. Now, before we multiply things together, let's look for any factoring we can do. And you could even factor before we get to this point, but certainly before we actually multiply things together, let's at least get the factoring done before that. Now, there's nothing here we can factor out. 7 and 9 are just numbers, but we could factor out a 4 here and here. So we're going to get this. And now we'll multiply things together. And we do see some cancellation. We can cancel out gx plus 5. And so we'll be left with 9 over 7 times 4, or 9 over 28. All right. So let me do another one. And just like with multiplying, again, that factoring is going to be very key to getting things to cancel out. So let's say we have this. It's 14. Let me double check here, make sure I didn't write anything down incorrectly. Looks good. All right. So again, KFC. We'll keep this one, we'll flip this one. We're going to change this to multiplication. This will be y squared plus 4y minus 32, y squared plus 14y plus 48. We're going to change this to multiplication. Now, if we went ahead and multiplied these, this times this is going to be a monstrous polynomial. Same thing here. This times that will be another monstrous fourth degree polynomial. And then trying to do any reducing with that could be very difficult. So let's reduce before we multiply things together. And that means factor, 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 and factor. Now, all of these have invisible ones in front of the leading term. So that means all of these we can solve or factor really using the guess and check method. So for this one, two numbers that add up to 4, multiply the negative 21. 7 and negative 3. Now for this one, two numbers that add up to 3, but multiply the negative 28. 7 and negative 4. Now for this one, two numbers that add up to 4, multiply the negative 32. 8 and negative 4. One more. There we go. Two numbers that add up to 14, but multiply to 48. 6 and 8. And there we go. So we factored everything, broken down what's going to cancel. Well, we can cancel things before we even multiply. Y plus 7's, gone. Y plus 8's, gone. So far, so good. So with y minus 3, y minus 4 times y minus 4 over y plus 6. So we multiply these together, and you can see it coming. You can see what's going to cancel before we stick it all together. And if you want to cancel, say, here and here, that's perfectly fine. Being a little, as they like to say, pedantic. But sure enough, y minus 4, that's also going to cancel. So what are we left with? Y minus 3 and y plus 6. And that's it. We're done. So just a couple points I want to make in this section here. Again, this is 6.1, and then I'll take a short break, and then we'll do a session for 6.2. But just evaluating these. For example, if we have something like this. Let's say we do this one. let's say we're supposed to find f of x equals 0. Or, I'm sorry, f of 0, not f of x. F of 0. So what we've done is we replaced x with 0. So that means on the other side, we're going to replace all the x's with 0. So instead of 3 times x, remember when 3 is next to x, it means 3 times x. We're going to get 3 times 0. Got a 0 in there, we get 3 times 0. And then we're going to have 0 squared minus 13 times 0 plus 36. So 3 times 0 is 0. So 0 is on top, which is totally fine. 0 squared is 0. 13 times 0 is 0. And then we're adding 36. So 0 minus 0 is 0. And if we add 0 to 36, we just get 36. So we just get 0 over 36. Now, if I have nothing and I divide it amongst my 36 friends, what do my 36 friends each get? Well, nothing. I didn't give anything to them. So that means the answer, f of 0 equals 0. Now let's say we had a different number. Instead of x be 0, let's say it's negative 2. So again, I'm going to use my other pen here. We're going to replace x with negative 2. So this will be 3 times negative 2 over negative 2 squared minus 13 times negative 2. And then finally we add 36. Now, what we can follow again is our PEMDAS, parentheses, exponents, then multiplication, division, then addition, subtraction. Now, when we're doing these complicated expressions, we're going to save this big division at the end. We're going to save it for the end. We're going to do it last. So reduce the top to a number, then simplify the bottom to a number, and then divide those two numbers. So on the top, what we're going to get is negative 6. So we're done with the top. We've turned it into a number. Now on the bottom, it's more complicated. We've got exponent, a multiplication, a subtraction, and an addition. So let's follow PEMDAS. Exponent. Well, negative 2 squared is negative 2 times negative 2. That's positive 4. So now, still working on the bottom, we do the multiplication. So you can think of this as 13 times negative 2, or negative 13 times negative 2. Now, if we think of it as negative 13 times negative 2, this entire thing, because negative times negative is positive, this will become a positive or a plus 26. But let's say we did it differently. Let's do it the hard way. 13 times negative 2, well, we're still subtracting. 13 times negative 2 would be negative 26. So only this part would become negative 26. This minus is still here. Now, of course, the easy way to do this is just make this into plus 26 and get plus 26, because you see what's going to happen. Negative and negative will become positive. And that's what happens in our next step. So you get plus 26, plus 36, 30, plus 36. Or 66. And we want to reduce this. So 66 turns out to be 6 times 11. Now we can break this into 2 times 3. Maybe we don't have to, because this could be negative 1 times 6. You don't always have to break things down into prime numbers or products of prime numbers, but that doesn't hurt. But in this case, we can see something canceling already. So the 6's will go away, and we'll get negative 1 over 11, or as we typically like to write it, negative 111. Again, we bring that minus sign out in front. So again, when we're evaluating these, we're replacing all the x's with the number we've chosen, and then we follow PEMDAS. And we do the division, we save that for the end if there's a division to be done. In this case, it's just reduced to a fraction. All right. So last thing to mention, and it has to do with simplification. I just want to mention this. Not all rational functions will reduce or simplify. Not all rational functions will reduce or simplify. So in the same way, like if you take 3/5, can't be reduced any further. You'll get rational functions that are the same way. So for example, so if we look at this, in the top, there's nothing that's going to factor out. There's nothing in common to both these terms that will factor out. Same thing with the bottom. There's nothing between these two terms that will factor out. And likewise, there are no cancellations. 2x plus 3, we treat it as like a single piece. So you can't cancel the 2x's like this. That's not going to work. You got to try to cancel this piece with this piece, and they only cancel if they're the same. Because they're not the same, not going to cancel. So in this sense, what the book will say, it cannot be simplified. That's as far as we can go. So that's it for section 6.1. 6.2, we'll of course be doing that next. adding and subtracting, and I mean, it's not too bad. We'll be talking about finding LCDs, and there's sort of a slick trick for doing that too. But again, if any questions, let me know, and hope to hear from you soon.